Hopefully the tractor starts.
Okay. Anybody have any questions? Well, I forgot to give you homework, so you don't have any questions. I just noticed that yesterday. All right, so we have a quiz at the end of class today. We're talking about property relationships. I've sort of given you what you need to know about tables. So we've been discussing property relationships. And that's included talking about tables. And anytime you're using tables, there's a good chance you're going to have to use linear interpolation. So that's where we've been. As far as getting values out of tables, if you have, if you're looking for material properties for a saturated liquid or a saturated vapor, how many properties do you need to know in order to look up the others? That's right, one. So that's really important. That's an important distinction. If you're away from the saturation point, a compressed liquid or a superheated vapor, then how many properties do you need? Two, right. And so those last two categories are the ones where you have to use that two-dimensional interpolation. And the last connection is we talked about quality. Okay, quality is how much vapor and liquid you have. So quality, talking about a material's quality only makes sense when the material is between saturation points. Okay, it doesn't make any in the dome, right? In the dome. It doesn't make any sense to talk about the quality of a material that's a compressed liquid or a superheated vapor. Okay, so if you see a problem that mentions quality, you know you're in the dome, the vapor dome. Okay, so now what we're talking about is we're going to get into some, well, if you had tables for every material that you ever wanted, then we'd kind of be done talking about property relationships. You could just look it up. But there are going to be mixtures of materials that you don't have tables for. There'll be, materials you don't have access to tables for. And so sometimes you need other ways to go from this property to this property at a certain state. And so we're going to talk about two important simplifications. So two important material simplifications. The first one is incompressible materials. And this is almost always just going to be liquids. You can use it sometimes for solids, but in this class, we don't care about solids really anyways. And the second one is going to be ideal gases. And you can almost always, anytime we're talking about a gas, you can almost always use the ideal gas simplification. So before that, I just have to introduce two new quantities. So I have to introduce enthalpy and specific heats. Okay, so the first one is enthalpy. Mostly don't think of enthalpy. I mean, some people introduce enthalpy as kind of like a physical thing, but really it's just a mathematical artifact that pops out of some equations we'll see pretty soon. Just think of it as like as a mathematical byproduct. It just shows its face in a couple different ways in a couple different equations. But for the people who do like intuitive ideas of things, you can sort of think of it as roughly the internal energy plus the work required to make space for it, wherever it is. Okay. So it's kind of like the difference in energy between this thing being there and not being there, you know. And we'll call enthalpy capital H, and its definition is internal energy plus the pressure times the volume. And the units of enthalpy are units of energy. And we'll often use the specific enthalpy, and that is a value that's given in the tables. And we'll call that lowercase h. It's just the enthalpy divided by the mass. And you can also calculate it as the specific internal energy plus the pressure times the specific volume.
How do we know that that's specific volume?
Because it's lowercase.
Got it.
Yep. And so that specific volume is volume per mass, which is the reciprocal of density.
Got it.
And specific volume is also a column in tables. So, and you know, it's kind of like redundant information in a table, because if you know where you are in a table, there's a column for specific enthalpy, so you can look that up. But you can also look up specific internal energy. You can look up pressure, and you can look up specific volume. So, and those have to exactly match. It's a definition. So there's really no need for that to be there, but it is.
But I mean, we're going to be working with tables provided to us that don't have all these values, some of the values.
Those are pretty standard things to be in every table.
Okay.
And so it's really just a time saver, because a lot of times you want the enthalpy, and so it's a pain in the butt to have to
just
calculate it. Yeah.
Okay.
And so that's enthalpy. And then the second new thing that we have to introduce is specific heats. And this all comes from a very complicated pair of definitions, but we're not going to use the complicated version. We're going to use simplified versions. But these are the definitions. And if you can remember it, it would be great. So lowercase c sub v is defined as, get a load of this. Try to wrap your head around the physical meaning of this one. The partial derivative of specific internal energy with respect to temperature with the volume held constant. I have no intuition about what the hell that is. And then there's also a C sub P that's defined as the partial derivative of specific enthalpy with respect to temperature with pressure held constant. We won't use this form. But this full form is used in calculations of table values, and like down the road you might take classes where you have to use those full versions. So we won't use this full form. We'll use simplified forms. So in certain cases, these can be simplified. And so now that we've defined those two things, we can get into incompressible materials and ideal gases. So first one, incompressible material assumption. This almost always is valid for liquids. Sometimes you can use it for solids, but in this class we're not doing anything with solids. It really doesn't ever work for gases. And the assumption, like kind of the defining assumption, is that the specific volume is a constant. And with the specific volume constant, you also get that the specific internal energy is just a function of temperature. So so generally, I mean, just generally speaking about a material that is not at a saturation point or in the vapor dome, specific internal energy, like any other property, depends on two properties. If you know two properties, you can calculate it. This is saying that since this thing can't be compressed, no matter what pressure you're at, that specific internal energy only depends on the temperature. Okay. As a consequence of these assumptions, C sub V and C sub P are equal to each other, and we just call it C, we just call it the specific heat, and it's just the full derivative of the specific internal energy with respect to temperature. So we just call this the specific heat. We don't worry about the P and the V anymore. And this lets us calculate some stuff. Well, first, let me show you why this works. So if we're assuming, so let's think first about C sub V. Okay, that's defined as the partial derivative of U with respect to temperature for a constant volume. But since U is only a function of temperature, this is a total derivative because U is just a function of temperature. And since it's incompressible, we don't have to state that V is constant. V is always constant anyways. So because this is always constant for an incompressible. And then for Cp, this is the partial derivative of H with respect to temperature with P constant. We can break up H into its definition, specific internal energy plus P times specific volume, d temperature. And now, because U only depends on temperature, we can break this up into du d temperature plus the partial of PV with respect to temperature for P constant. I sort of glossed over here that we lost the P constant requirement because U doesn't depend on P anyway, so who cares? And then this one, well, we're requiring that P stay constant. V is already constant, so it's not going to change. PV is constant for an incompressible material with constant P. And so we get that Cp also is just equal to du dt. Okay, so that's why that works. Now this thing, du dt, allows you to calculate the change in specific internal energy for a given change in temperatures. So let me show you how that works. Let's say that we have 2 kilograms of liquid water. And it goes from 320 Kelvin to 324 Kelvin. As pressure goes from 1.01 times 10 to the 5 pascals to 1.40 times 10 to the 5 pascals. And we'll assume that the specific heat for water in this temperature range is 4.18 kilojoules per kilogram Kelvin. And we want to calculate the change in internal energy and the change in enthalpy. Okay, well, first, I guess I'll do all this in SI units. So this is going to be 4180 joules per kilogram Kelvin. And so we have du dt is equal to 4180. And now this is called a separable differential equation. You can think of just integrating this with respect to temperature, or the way I like to think of it is multiply both sides by dt. You get du is equal to 4180 dt. And now we can integrate both sides. So we have the integral of du is equal to 4180. Well, let's write it like this. And the boundaries for these are state 1 to state 2 in both cases. So what we get is a change in specific internal energy there, because it's, you can think of it as, well, let me write it like this. We're going to do a lot of these. So you have U evaluated from state 1 to state 2. And that's equal to 4180 times the temperature evaluated from state 1 to state 2. And so what you get is that the change in specific internal energy is equal to 4180 times the change in temperature, 324 minus 320. And so the change in specific internal energy is 16.72 times 10 to the third joules per kilogram. And so now if you want the change in internal energy, not the specific internal energy, just multiply that by the mass. And you get 33.44 times 10 to the third joules. And then that's something you could use in the first law. Okay. Notice that this was, so if you are using a water table, a table for compressed liquid water to do this calculation, you would need this to look it up. In our case, those pressures never came into it because we're assuming it's incompressible. But what you would see is if you plug this into the table and went through the effort of dealing with the pressure and stuff, you'd get values that are almost exactly this. Okay. Now we need the specific enthalpy.
Sorry, really quick.
Yeah.
So that change in pressure, like that nominal change in pressure, that's just because of the water expanding and contracting?
Well, this pressure, I just gave it to you as, this is like some information we know. But it turns out if you're assuming that this is incompressible, just remember that none of this stuff depends on the pressure. We are going to use it now to calculate the change in enthalpy.
Okay.
So the change in enthalpy is equal to the change in specific internal energy plus the change in pressure times volume, specific volume. That's from the definition. Since we're assuming this is incompressible, we're assuming that the specific volume doesn't change. And so we can write this change in specific enthalpy as the change in specific internal energy plus V times the change in pressure. So the change in specific enthalpy is equal to what we just calculated for this. So 16.72 times 10 to the third plus the specific volume times the change in pressure. So now this is where the pressures come in. So 1.40 times 10 to the fifth minus 1.01 times 10 to the fifth. Okay, what are we going to do with that specific volume? What you want to do in this case is so we're going to treat this as constant, okay? Specific volume we're going to treat as constant because we're saying it's incompressible. But that does change a little bit over ranges in temperature. So what you'd like to do ideally is look that up for something around the range of temperatures that you're dealing with. Okay, so, and since it doesn't matter for an incompressible material whether this is a compressed liquid or a saturated liquid, just use the saturation table here. So we'll use the saturated liquid water table. To choose a specific volume in the correct temperature range. And we'll see when we look at the table that it doesn't change unless the temperature variations unless you go to really different temperatures, but you might as well use it from something close to the right temperature. Okay, so let's go to the let's go to the saturated liquid water table and find a specific volume for somewhere around a temperature of 320 Kelvin, which is the temperature range we're dealing with. Anyone know what a ballpark figure is for specific volume of water? Well, think it's the reciprocal of the density. Anybody know what the density of water is?
It's like almost exactly a gram per milliliter.
Yep, and so that is 1,000 kilograms per cubic meter in SI units. And so we're looking for a specific volume that's about 0.001, about 1/1000th of a cubic meter per kilogram.
it's like 0.9998 or something.
Let's find out. Okay, so I'm going to water index by temperature because I want the right temperature range. And I want, well, I have it in Kelvin for some reason. So 270, what's 320 minus 273? Or
47.
Okay, so yeah, somewhere around 50, 47, 50. We'll see what they have. They have 50. So go to the specific volume, and it is 1.01 times 10 to the minus third. So 1.01 times 10 to the minus third meters cubed per kilogram. So plug that in. And our estimate for the change in specific enthalpy is 16.72 times 10 to the third plus 1.01 times 10 to the minus third times 39 times 10 to the third. My scientific notation is all over the place here, but we get a change in specific enthalpy of 55.72 times 10 to the third joules per kilogram. Then multiply that by the mass to get the change in enthalpy of extensive enthalpy, and you get 111.44 times 10 to the third joules. Okay. Our calculation for the change in internal energy, that's something we can use already. You know, like we can use that in the first law of thermodynamics. The change in enthalpy, we're going to get to an equation soon, calculations where we can use that. So far, we don't have a way to use that.
And that was just the heat transfer between states 1 and 2?
Yeah, yes, that was just, we don't know what happened between those two states. We don't know how it went from here to here, but we do know that the temperature and pressure changed in that way. All right, let's do ideal gas. Just talk about it quickly. So the ideal gas law. We are going to use this in a little bit of a different form than you've seen it in chemistry, and the reason we're going to do that is because it is in the form where we can plug in values from the tables and plug in values that we're going to talk about all the time. So you're used to seeing the ideal gas law in this form, most likely. Pressure times volume is equal to the number of moles times the molar ideal gas constant times the temperature. And if you wrote this in terms of specific values, you could write this as the pressure times the specific volume per mole is equal to the molar ideal gas constant times the temperature. For us, we're not going to use this universal gas constant. So we're going to reformat this equation using a non-universal gas constant. So whatever material you have is going to affect the R that we use. And that is R. So the one, this is where it can get a little confusing because in chemistry, you've used the universal gas constant and you've written it without this overbar. Now, when we think of it per mole, the universal gas constant is per mole, we're going to write it with the overbar that indicates it's a per mole specific value. And the one we're going to use is not going to have the overbar. So it's going to look like the one used in chemistry, but it's something else, okay? And this is equal to the one that you are used to, the universal gas constant, divided by the molar mass of the material. So this M is the mass per mole of our specific gas, the one material that we happen to be using in that problem. And so for us, the ideal gas law is going to be pressure times specific volume is equal to RT. But the nice thing is, once you've calculated that, that value of the gas constant for the gas you're using, P, V, and T are all things that are in the table for the state that you're at. Okay, and we're going to go back and talk more about what you know for an ideal gas, about internal energy and stuff like that on Monday. Anybody have any questions about this yet? I forgot to give you homework last time, so I guess the homework is probably just going to be linear interpolation. Maybe I'll give you one problem on this or something like that. But okay, that's all.